Hi, in this video, we want to take a look at autoregressive moving average models where we're going to focus on estimating the coefficients of the autoregressive part and the moving average part. Specifically, we're going to do this through maximum likelihood estimation. All right, so maximum likelihood estimation, just like the words say, we're going to estimate the coefficients by using some theoretical beliefs about the situation. And in those theoretical beliefs, I'm going to get a probability distribution, and I'm going to maximize the likelihood off of the theoretical distribution. And that's exactly maximum likelihood estimation. All right, now, there are tons and tons of ways to estimate parameters of a model. The two major ones in statistics are method of moments and maximum likelihood. Okay, method of moments, that's more of a systems of equations way of doing things. It's a great way, has a lot of uses, it has a lot of drawbacks. Maximum likelihood estimation is more of a calculus way of handling it. And if you work through a stat theory course, you'll be very familiar with it, and it'll feel very natural. But it's very heavy on the calculus aspect, because we're going to be maximizing a probability function. Okay, and so that's our two major ways to go about it. Now, method of moments has two major disadvantages in that, one, we can get an estimate that isn't even in the parameter space, which I showed in a previous video, and it will typically have greater variance than maximum likelihood. Okay, but it feels very natural to us if we're comfortable with systems of equations. And it's easier to see the correspondence between our estimate and the actual theory that we're building up. Maximum likelihood estimation doesn't have the problem of outside of parameter space, and it typically has lower variance, but it's a lot more calculus, and the calculus can get kind of hairy at times. And it's still only differential calculus, but you know, choose whatever one works best for you. I usually go with maximum likelihood estimation professionally. If I need an initial estimated value, what I typically do is go to method of moments, get the initial estimate, drop it in, kick off the algorithm, boom, get a good estimate. That's usually how I proceed. All right, so we're going to run through some examples from time series analysis and its applications. Chapter 3, section 3.5. Here are the names of the authors. Here's our GitHub page for you to check out. And UCF students can download the textbook for free through a Springer link on the library's webpage. All right, so what we're going to do to get a feel for what's going on, to get a solid understanding of the approach that we talked about with maximum likelihood estimation, we're going to start with an AR1 process. Why are we starting here? That's as easy of a time series model as we can get, and we'll see that it's going to get pretty juicy just off of this. Now, this literally follows the same script from your theoretical statistics course if you've taken it. So this is going to feel very similar to what you saw there. Now, if you haven't taken theoretical statistics, this is as gentle of an introduction as I can build up for this. And you'll hear a lot of the same phrases and terms. And so keep with me, because you'll get more comfortable with these concepts so that when you see this material later in a theory course, it will be more comfortable. All right, so we're going to focus on AR1 process. So let's go ahead and say that x of t is equal to the overall population mean plus our only parameter times the difference between the previous observation and the overall population average plus our white noise term. All right, now, previously in the videos, we have always said that mu was equal to 0. Here, we're just releasing that just a little bit, it doesn't really change much from our point of view as we work through this, because the mu is just changing, it's just shifting our time series up and down, doesn't change the statistical properties otherwise. Now, something we're going to do is that we're going to go ahead and make the assumption that that coefficient is less than 1. That gives us a lot of nice mathematical properties, and it'll make things for the proofs work out better. And we're going to go ahead and say that our white noise is independent, identically distributed normal with mean zero constant variance. All right, so now I've collected my data off of my visualizations, off of my subject matter knowledge, off of my understanding of what's going on and talking to my stakeholders. I believe that an AR1 model is the appropriate model for my time series. Okay, so now I need to estimate my model. I need to estimate that phi. Okay, so the approach that we're going to do, we're going to find a likelihood function, and then we're going to maximize that likelihood function. Okay, so likelihood functions and densities are equal to each other, but they take different points of view on what's inside the functions. All right, so a density function, here this is the probability distribution function that we've got. Here, the observations are the variables. So these x's are all observations, and they are the variables. So here we're dealing with the density before I see my data. And the parameters are treated as constant values. So, and I'm in the situation when I deal with this type of function, the densities, my data has not been collected yet. I'm trying to have theoretical understanding of what's coming down the pipe towards me. Now, the likelihood functions, I'm actually going to take pencil and paper, the same equation, the same function, but this time, these x's are going to be treated as constant values, because now I've observed my data. There's no longer a mystery of what the x's are. Those are constants because I have them in my hand. I've already collected my data. I've recorded it down. Those are hard, firm numbers. But I don't know the parameters of that equation. And so I'm going to treat the parameters as the variables. Okay, so now when I think about that, when I look up here, the observation aspects are constants and the parameters are the variables. So now I've turned the equation on its head. I've flipped everything out. It's like Freaky Friday. Everything is reversed. It's like the mirror dimension with Mirror Master from DC Comics, arch villain of the Flash. All right, so when I look at the density function, we normally write that down with an F, and we put down a bunch of x's, and you notice that here, these are the variables of the situation. On the left of that given symbol, these are the variables, and these are the parameters of the function. Now over here, I have my likelihood function, and you'll notice I'm writing things just a little bit different. I've switched the order of this. Now, here, these guys are the variables of the situation, and this is the set of constant values because these are the constants after I've observed my data. So from an algebra, write it down, pencil and paper point of view, likelihood function and density function are the same thing, but I'm treating what goes in there into the function in differently depending on am I pre or post data collection. Okay, so now what we're going to do, we're going to say that we have an AR1 model. This means that each observation is dependent on the prior observation. Okay, so this is where things get a little bit different than your stat theory course. In your stat theory course, you always make the assumption of independent, identically distributed. We don't have independence. We don't have identically distributed. Why? Because it's depending on the past observation. Okay, so This equation is still correct, but I know that the distribution needs to be broken up. So remember, when I have independent, identically distributed, and I'm dealing with the density, I just factor it out. I factor each individual x part into its own individual function. Here I'm going to do that also, but I have to consider the fact that each observation depends on the past one. Okay, so here, x of 1, there's no past observation, so it doesn't depend on anything. So when I do this factorization on the right-hand side for the x1 part, it's just by itself. Now, when I think about x of 2, it depends on x of 1. All right, so here, when I want to factor out the x sub 2 portion of this, I need to include x of 1 because in this scenario, it's my data is sequential. If I'm thinking about x of 2, x of 1 has already happened. So it's in fact a constant. And so I need to put it in that constant group. Now, when I get to the x, when I factor out x sub 3 portion here down to this, I have to consider x sub 2. Well, you could say, wait, whoa, Smitty. X sub 2 depends on x sub 1. X sub 1's been observed. I should have x sub 1 also. That would be a good point. But this is AR1, and because of the buildup of what we're doing, knowing x1 when we know x2 does not provide additional information for this. So I'm not including x sub 1 in my constants on this part. And so I only include the last observation inside the constants as I work through this. And so you can see this chain, x sub 2 and x sub 1, x sub 3 and x sub 2, all to x of n minus 1. And every single time I include the parameters. All right, so here, this tells me the pencil and paper version of the likelihood function. Now, so this gives me a way of writing it out and gives me a way of tackling it and invoking what I know about the density and putting it on paper. Now, when I look at this, when I want to treat it as a likelihood, now that I've done my factorization, what I'm going to do, I'm going to take whatever I get from all of this, after I write it down, after I put it in nice, college algebra, pre-calculus, writing it down. You notice I haven't done any calculus. I haven't done any derivatives or anything like that. I haven't done any logarithms or any slick stuff like that. I've just wrote down the equation. So now, what I'm going to do, when I look at an x, I'm going to go, that's a constant. When I look at mu, that's a variable. When I look at phi, that's a variable. When I look at sigma squared, that's a variable. Now, something that we're going to do, we're going to treat sigma squared as a variable instead of sigma by itself. It's a slight difference. This makes the calculus just a little bit easier. So this is the standard way of proceeding. So when we see the sigma squared, the sigma squared is the variable, not sigma, even though there will be a direct relationship. All right, so now what we're going to do is that we're going to isolate my white noise term in the process, the equation that we have up here. I'm going to isolate my white noise term. And we're going to, consider that it's identically distributed white noise, constant variance. All right, and so just doing that, I'm just rewriting some stuff. Now you'll notice that, hey, this is giving me, all right, if I just kind of, look at this in another way, I'll notice that this is the same as saying x of t given x of t minus 1. Here is that expected value that I have, and I'm getting that constant variance using just the standard normal properties. All right, and so in doing this, by setting it up this way, I realize that this the density of x sub t, is in fact a normal distribution where I'm doing a horizontal shift on the normal distribution with the appropriate variance value. And so here, this tells me what each of these terms are equal to. And so now I can go in and drop those in. So I figured out everything except the very first one from there. All right, so now I notice I've got multiplication here, and this capital pi means multiplication. Remember, capital sigma means addition, capital pi means product, multiplication. And so I'm going to replace each of these f's with this normal distribution that I get. And I'm going to be, I can see that there's a bunch of multiplications. So I'm making it more compact with the product notation. And so here I replace all of this jazz with this. And then I'm going to go ahead and replace the f with the normal distribution. All right, so now I'm going to realize that I have a constant here in my multiplication. I'm multiplying n minus 1 terms all together. And in those terms, I have a constant every single time. All right, well, with that constant, I can rewrite this as n minus 1 of those being multiplied out together. And so that gives me this part. Here, I realize I have an exponential. All right, well, if I'm multiplying exponential, that converts the exponent to addition. And you'll notice that, boom, I have addition on the exponents. So now I've collapsed this down very nicely. Now, if you're not familiar with this type of work, this looks like a huge, ugly equation. And you'd have a good point. But we're going to keep on rocking this. So now, here I'm replacing E with EXP just because it's just ugly notation up top in the superscript. So I'm bringing it down using EXP instead of E. All right, only difference there. Now, I've got all of this I'm figured out. Like, I know exactly what it is from a theoretical point of view. I need to work out the details on x of 1. All right, so what we're going to do, remember, we made the assumption that that phi was less than 1 in magnitude. Well, if you remember from a previous video, that means our AR1 process is causal. And since it's causal, I can immediately take the relationship between x and a series of the white noise terms, and let's go ahead and do that. All right, so now also remember that x of 1, normally distributed, here's our expected value, and because it's AR1, here is the variance. All right, and so now I'm using that causal relationship to get the series connection between my white noise terms and x of 1. Okay, so what I can do, once I have this representation, I can go through and take the expected value of both sides, and we can see that the expected value is equal to mu, just like I said a moment ago. Now the variance, of course, I'm going to be doing a product. Now, first I have the variance of this term right here. That's a constant that is not going to influence the variance whatsoever. So I kick that out. Now I'm going to have the variance of something with expected value 0. So that's just going to be the variance of that squared. So I have this. I want the expected value of this thing squared with itself. Now notice that I put in different subscripts when I do this. Here I've got J. Here I've got K, because when I do my multiplication, I don't want to get them all jumbled up. All right, so then I get, just using the standard formula with summations and multiplication. This is just using, distributive property from your, middle school algebra class, literally the same thing. All right, so when I get to this, now I'm going to break this up. So realize that I've got the case when J is equal to K inside the summation. I have the case where J and K are not equal to each other. So I'm going to break those up. So remember, when I have expected value of addition, that is addition of the expected value. So I'm going to take all of the J equals K cases in one summation all of the j does not equal k cases and put that in a different summation, and I'm going to break up that expected value. Boom, check this out. All right, so now I've got this where j and k are equal to each other. Notice that I've got a square in there and I got a square there. That's not a coincidence. And here I've got these different terms, and we know that j and k do not equal each other. All right, so now expected value of a sum is the sum of expected values. So I know I can pull the summation and the constants out in front of my expected value by the expected value properties. All right, and I'm doing the same thing here. Just make this a little bit easier. Now, I'm looking here, I've got expected value of white noise squared. That looks a lot like a sigma. Here, I've got expected value of different white noise terms. That's going to be equal to 0. Boom, look at that. Look at this, like clean it up. It's so nice. All right, so now this corresponds to that. I look here, I go, hey, wait, whoa. I have an infinite sum of something to a power. So I've got an infinite sum of phi squared to the power of j. That's a geometric series. Boom, we know how to add that up. This is equal to this as long as phi squared is less than 1 in magnitude, which it is because we made that assumption in the beginning. And so now I know that it's normally distributed. I know its expected value, and I know its variance. I know what this f is supposed to be now. So I'm going to replace it with the appropriate normal term. I replace this f with the correct term. And, you know, it is a little bit ugly. I replace it with all this stuff. See if I can get the mouse to highlight it. I replace it with all of this. Okay, so now it looks like a lot. But at this point, I'm literally just doing college algebra. I personally did this by hand before I made the video. I worked through all the details of this. It looks ugly, but it's doable. Everything is correct. And I'm just going through here, and now I'm just rewriting things in a neater format. And I get down to this. Now, I mean, it looks like a lot. It honestly is. It is quite a bit. But what we can do is look here. You know what? I'm going to go ahead and call this S right here. This whole thing is just S of mu phi. And you'll notice all of a sudden that formula collapses very quickly. All right, and so we're going to call that S our unconditional sum of squares. Boom, we've got it right here. All right, so now when I look at this, I want to maximize this likelihood with respect to the parameters. I've got 3 parameters. I have mu, I have phi, I have sigma squared. Okay, so when I maximize something, the standard way to do it, if I can, of course, is going to be using calculus. I'm going back to Calc 1. Easy peasy lemon squeezy. All I'm going to do is take a derivative. Now, when I do this, I'm just going to go through, do the standard trick that we normally do. I realize that when I look at this, I've got sigma squared here. I've got sigma squared here. Okay, everything else, when I'm taking a derivative with respect to sigma squared, everything else, all the mu and the phi, those are constants with respect to the derivative. So this is a much easier problem than it looks like. I just have to do a little bit of product rule, all right? And taking a derivative with e, take a derivative with e is the easiest derivative we possibly could. Got a little bit of chain rule in there. Boom, boom, boom. We got this. All right, so now, after I take the derivative, and I work this out by hand also, it did take a good amount of paper for me to work through this, but I worked through and got it. I think this is the way the book presents it. I'm not 100% sure. I forgot what the author said. All right, so check this out. I've got all of this times this. All right, so let's check this out. Can that be equal to 0? So I'm taking the derivative. I want to maximize. So I need the derivative to be equal to 0. Okay. Can that be equal to 0? No. Can this be equal to 0? No. Can this be equal to 0? No. Can an exponential be equal to 0? No. Can this be equal to 0? No. All right, so I notice that for equal to 0, all of this is not helping me. All right, well, I get to here. Can I make that equal to 0? Yes, I can. All right, so that part, this is the punchline right here of this entire derivative is that. Okay, so I look at that and I go, hey, I want that to be equal to 0. Well, you know what? I'm going to go ahead and set this equal to 0. And what I get for sigma squared is going to be my estimator. All right, so this means that this unconditional sum of squares, where I put in my estimated mu, my estimated phi over n, that's going to be my maximum likelihood estimator for the variance of that white noise term. All right, now we're getting somewhere. We got our first estimator out of this. This is great. All right, now, something about this. This is a biased estimator. You know, some statisticians are like, oh no, it's a biased estimator. It's not that big of a deal. If I have a decent size of data, it's not going to be that far off. You know, the bias isn't going to be a big deal. But if you really, really, really worry about the bias, divide by n-2 instead. All right, you technically won't have maximum likelihood. It'll be an unbiased estimator. You can trade off. Heck, if you want to do n-1, and that way it's neither maximum likelihood nor unbiased, but do whatever you want to do. It's not that big of a deal. But if we change n to n-2, we get unconditional squares estimate that's unbiased. All right, so now if you remember from your Calc 1 class, you're like, but wait, Smithy, derivatives. Derivative equals to 0. It could be a maximum, a minimum, or an inflection point. How do I know which one it is? I got you on that. We don't have to do a second derivative test on this. Why not? We could. It would work out, and we would get exactly what we want. We would get, we would get a negative second derivative at this value if we did it, but we don't need to. Why? Because this is a probability function. All right, so I know to the left, this probability is it's based off a normal distribution. I have far to the left, it's going to be going asymptotically down to 0, and it's always positive. So I know it's monotonically going down to 0 far to the left. Similarly, far to the right, I know it's going down to 0 on the right, and it has to keep on going down. Why do I know that there's no bumps or anything? Because there was only one derivative. This function is a smooth function. So I know that there's only one peak on this whole thing. Also, I know this is always positive, and I know that it has to go down to 0 to be an integrable function to correspond to a probability distribution in the first place. So I don't need to even bother with the second derivative. Wouldn't you love that situation when you were in Calc 1? Just to be like, hey, from my knowledge of the function, I don't need to. I got it. Done. All right. So now let's go ahead and consider what we want to do for mu and for phi. Okay, so logarithms are monotonically increasing functions. That means if I take a function and maximize it, or I take the log of that same function and maximize it, the maximum point will be the same value either way. Why do we care? What I'm going to do is, if a logarithm would give me an easier function to work with for that derivative, I'm going to work with the logarithm version instead of the regular version because it makes my life easier. I have the option of regular likelihood or log likelihood, whichever one is easier for me. Okay. In fact, any monotonically increasing function that is differentiable would work for this. So if I wanted to, I could use maybe square root instead of logarithm. If that worked out for my probability function, my likelihood, I should say likelihood, that's better wording. But logarithms by far are the most common ways, and we can bust through some tougher problems this way. And so this is why your Calc 1 professor made you go through the logarithm stuff that they made you go do. All right, so my calculus will be easier if I work with the logarithm on this one. Okay, so what I'm going to do, I'm going to take the log of my likelihood, and which is just equal to this. Okay, so now logarithms convert multiplication to addition, and you can see that's exactly what I'm doing here. They convert exponents to coefficients, and you'll see that's what is happening here. Things are just like or the inverse of log is exponential, so that's cleaned up nicely. And so now I'm just rewriting a few terms, working it out. Now, what I'm going to do, I'm going to replace mu and phi with my estimated values, okay, because that's my ultimate goal. Now, something to pay attention to, I'm replacing the phi with phi hat because I'm trying to find an estimate. I'm going to, this is a constant, doesn't matter for this purpose. All right, I'm replacing sigma squared with my estimate of sigma squared. I'm replacing mu with my estimation of mu, replacing phi with my estimation of phi, and I'm replacing sigma squared with my estimate of sigma squared right here. Okay, so I notice that my estimated values cancel out on this. And so this portion here becomes a constant, which is going to be important in a moment. Now, I've worked out all of this all so far. So I've cleaned this up very nicely. And I rewrote this in a particular manner just so that things are easier to see what the next step is. All right, so I just rearranged terms. I haven't changed anything. I just did a little bit of college algebra. Okay, so now, if I'm trying to maximize something or minimize it, constants don't matter. Okay, so a constant value is not going to change the point that gives me the maximum on this. Okay, so these terms for the purpose of maximization are not important. Okay, and also this n over 2 is not important also for the purpose of maximization. All right, so now what we're going to do, I am going to look at that negative sign. I'm going to drop the constants here. They don't change the point of maximization. This n over 2 is not going to change the point of maximization. And so I'm going to drop that also. So I'm going to focus in on what's in the square brackets. Now, that's what's down here. You'll notice that there's a negative sign that's right here. All right, so up until this point, we've been focused on maximization of this. Well, what I'm going to do instead, I'm going to multiply this combination by a negative sign, and that's going to give me this. And what that's going to do is, in fact, instead of doing a maximization, it's going to be a minimization. Really, there's no need. I could have kept it as is and done maximization. The authors of the textbook present a minimization example with computer code, so I went ahead and followed what the authors did. Theoretically, it doesn't matter either way. So what we're going to do is I'm going to use this function here, and my goal is to find values of mu hat, phi hat that maximize this criterion function. Now, if I look back at all this, there's a bit going on. There's quite a bit. So if I was to look through this, I was like, man, I wish I could simplify this. I wish I could just kind of shave this down somewhere, make it just a little bit computationally easier. Well, if I look at this, really conceptually, I've got two aspects of all these calculations I've got going. When I look through this, I've got x sub 1, which does not depend on any other values. Then I've got everything else that depends on previous values. So what I could do if I wanted to shave this down and lose a little bit of data, but not that much, I could actually kind of ignore the very first data point on this and then proceed. And you'll notice that here, like this part in my unconditional sum of squares, this is my x sub 1 part, which is very different from the rest. When I look at my likelihood function, I've got everything that's not part of x sub 1, and then I've got x sub 1. So it really would just make things a little bit smoother and easier for me as a human to work with it if I just ignore the x sub 1 term, which would be just dropping the first data point, which seems reasonable in a lot of situations, as long as I have sufficient data. And so let's go ahead and do that. So the authors call this x sub c. And basically, when I take this point of view, I'm playing exactly the same game, but I'm dropping that first data point. And so we end up just doing a little bit of modifications. It's the same game plan, same idea. And then we're going to be using these equations that we get to solve the problem. You notice that things are easier now, simpler to work with. I'm going to set alpha equal to mu times 1 minus phi. My estimate looks very much the same, but now I don't have that x sub 1 term in there. And so I've lost one data point, so I'm dividing by n minus 1, maximizing likelihood, but it is a biased estimator. There's a trade-off there. And so now what I'm going to do is I'm going to treat this like a systems of equations, and I'm just going to go ahead and work through this and solve things, in a very natural manner. And so here, alpha, just from my setup here, is going to, alpha hat is equal to x bar sub 2 times phi hat x sub 1, just rearranging some things algebraically, and then putting hats for estimators. And then x sub 1, I'm just taking an average using all the data points. X sub 2, I'm using an average with all but the first data point. And then I'm just working out those details, working through. And now I have an estimate of phi hat. And I have an estimate of mu hat. All right, so if I look at this, and so I take a good hard look at this, and I compare it to the Yule-Walker estimators and the conditional least squares estimators, they're going to be approximately the same. And the difference is how our endpoints are handled. Really, that's the true difference in what's going on. But my actual estimated values will be about the same. Mu hat, if I check this out, it's going to be pretty close to X bar, right? I mean, which is not surprising. And phi hat is going to be pretty close to our first autocorrelation value. Not surprising. And so if I want to, I can adjust my white noise estimator to be unbiased also. This time, make an adjustment for missing data points in there. And so in general, with AR models, maximum likelihood estimation, unconditional least squares, and conditional least squares are going to be analogous to this AR1 example. And we can slug through it and expand it, but it's more complicated, more work. Conceptually, it's the same ideas. Now, if I want to start working with ARMA models, it's going to be more explicit it's going to be more difficult to explicitly write down those likelihood functions. I did AR1 honestly because the likelihood function is just easier to write down pencil and paper. If I'm doing ARMA, what I'm going to do is I'm going to write the likelihood in terms of those innovations we talked about in a previous video. And then we're going to use one step ahead prediction errors like this. And I'm going to go ahead and just skip the material on estimating autoregressive moving average models with maximum likelihoods. If you read the textbook, it's pretty general. It's all mathematically correct. It's solid. It's good information, but I feel like it's not nailing things down enough to be really helping us learn anything. All right, so let's go ahead and just run through an example. Remember, we go through all this theory stuff that we have a better understanding of the real models that we build when I have real life data on the job employment coming in. And so I'm going to build an AR2 model on that recruitment time series using maximum likelihood. All right, so let's go ahead and set up our workspace here, making sure I don't have anything floating around in my workspace to pollute the computations. I'm suppressing the number of digits displayed and printed, and I'm saying avoid scientific notation if you can. All right, so now I'm loading the data from the ASTSA package, and now I'm using the autoregressive maximum likelihood estimate function, and you'll notice that this is a base R function, and I'm saying, hey, do order 2. And we reach the conclusion that order 2 is appropriate for this because we look at the autocorrelation function and the partial autocorrelation function and look at when they cut off or tail off. All right, so here is that X mean that we're getting off of it. Here are the coefficients that we're getting out. And now we can get our standard errors by getting the coefficients off of here. So now remember the standard errors will have a covariance between these two, between the two coefficients. So if I want to just look at each coefficient individually without considering the other, then I only want 2 at a time. I don't want to consider the cross covariance aspect. And so here I'm taking just the diagonal. I'm not considering the cross covariance. And so here's the variance of prediction for us. All right, so now let's talk about using Gauss-Newton to compute estimates. So let's say that I'm dealing with a moving average 1 model this time. So we're going a little bit different direction, different type of model. So here is my process. So I've got, I'm taking a white noise process and I'm taking consecutive values and adding them up in a certain manner to get my current time series. All right, so we're going to say that W sub t of beta is the error between our observed value and the modeled value immediately before we observe X sub t. So I'm in the situation that I've got t minus 1 observations. I want to predict the future value when I'm right before seeing it. All right, well, if I go through the work that we've done before and just work out the details, here, this is going to be that error term, X sub t minus all of this. And so the errors depend on the parameters. And for an MA1 model, we're going to say that the initial error is going to be equal to 0. And then I'm just setting it up. I'm reducing this down. So here, this is the general formula for the error. I'm reducing it down to our specific case. Like that. Okay, and so what am I going to do? I'm going to take the derivative with respect to the parameter. All right, so here that's going to be derivative 0 because theta is not there. I'm taking the derivative here. You notice that that gives me 1 in that position. Here I take the derivative, so I'm using product rule. Okay, and so I get this portion out. Now I'm going to use this assumption that we have here, and I'm going to apply that to here. So we're saying that this is a constant. So when I take a derivative, I get 0. And so now I'm going to set z sub t of theta equal to the negative partial derivative of w sub t. And off of this, that initial z is going to be equal to 0. All right, so now our differential equation gets reduced down to this. All right, so now, why am I doing this? I'm trying to set up the math so I can do that iterations in a second. I want to use Gauss-Newton. Okay, so now what I'm going to do, I'm going to work through my Gauss-Newton equation. All right, so Gauss-Newton, what we're doing, we're taking my current guess. I take my current guess, I'm going to take the function I'm interested in, take the tangent line at my current guess, and I'm going to find where that tangent line hits 0. That is going to lead me to my next guess. And so then I'm going to repeat that process. I'm going to take my next guess, find the tangent line on the curve, find where the tangent line hits 0. That's going to give me my next guess. All right, so the idea here, I'm going to make a guess. I'm going to use that guess to get a better guess. Then I'm going to use that guess to get a better guess. And then I'm going to use that guess to get a better guess at what the value should be. And under very mild assumptions, this is iterative process is going to ultimately give me a good estimate of what's going on, as long as the situation is relatively nice. And we're in one of those relatively nice situations. And so we're going to do a recursive equation, and here it is. It's kind of ugly. It looks bad. It's not that bad. It's just using exactly what I told you. I'm taking the tangent line in a kind of a funny manner and shooting down to where things equal 0. And so this gives me a way of finding the theta for an MA1 process. Okay, so now let's run through another example. Let's go ahead and look at glacial varve series. All right, so let's go ahead and take the glacial varve thickness from Massachusetts for just over 600 years. And the textbook states a case for first order moving averages models might fit logarithmically transformed in difference on our values. Okay, so what we're going to do is I'm going to take the log of the time series, and then I'm going to take the difference between those, and that's going to be the time series I work with. So I'm taking the difference of consecutive log values, and that is my logarithms. Now, why would this be interesting? Well, it's established that this difference of logs approximates the percentage of change. This is common in like financial engineering, by the way. And we're just going to borrow it from them. They're generous, right? Financial engineers, they've got money, they can be generous. All right, so what we're going to do after I get this, which is this log of the ratio, I can look at the ACF and the PACF plots, and I go, hey, that looks reasonable. Let's go ahead and do this. And so here, I see that I've got one large ACF, and okay, I didn't plot the PACF. The PACF kind of just trails off. And since it trails off, that tells us that this is a reasonable way to go. So from having just one ACF and then it cuts off, I'm thinking, hey, MA1 model is a good way to go. All right, so now let's go ahead and compute that. And so all of this now is just to work out the Gauss-Newton estimation. Honestly, this is not the best way to do it. Real life, if I was doing this for work, I would go through and I would just let the functions that have already been built do this for me in R. But this gives you a way to show that iterative process if you want to, roll up your sleeves and get into it. All right, and we can just see how it's progressing through the different iterations. This is a good idea if you need to do custom iterations. to check to make sure that things are going the way you want them to. And we can see that theta hat has converged. We can see after, see, 1, 2, 3, 4 iterations up to rounding, we get the same value that we're going to get after 19 iterations. So I'm feeling like this is probably converged. Yeah, all right. Here is our S sub C and S sub Z. All right. So let's plot the conditional sum of squares results. All right, so now check this out. What has happened in this is that here was that initial guess. And then here was that second guess that we got. Here was that third, fourth, fifth, sixth, and it just kept on going down and down. And it just kind of, we see that it's stuck. And so now we know that the value here is going to be the actual value that we want for our theta hat. All right, so now we want to look at the general case of causal invertible AR moving average models. All right, so maximum likelihood estimation and conditional and unconditional least squares estimates and Yule-Walker estimations for AR pure models all lead to optimal estimators. So this is good. What this tells us, and we're not going to prove this, if we were doing a pure proof course, we would dig into this. So what this tells us that it's a good idea to use these techniques, really. All right, so let's go ahead and use beta to represent all the coefficients in our autoregressive moving average model. And so beta is the vector of coefficients. And you'll notice I have my autoregressive, there's P of them, and then I have my moving average, there's Q coefficients. Now, here, get ready. Get ready for it. We're going to invoke central limit theorem. Why do we do that? All right, well, we're statisticians. Central limit theorem gives me a distribution to work with if I want to do hypothesis testing, confidence intervals, anything like that. You know, this is the lane of statisticians. We're getting deeper information out of the system than, you know, like a data engineer or computer scientist or the IT people, you know, get out of data. We have more information from our stuff because we have this theoretical background. All right, so central limit theorem. That tells me that we're going to have, under certain assumptions, certain situations, we're going to have normally distributed with a mean and a variance. Okay, now notice that beta was a vector. All right, so this means that this is multivariate normal. What we're saying is that my coefficients, I can figure out what is going to be the asymptotic distribution of my coefficients. So for large amounts of data, when I have the correct model built up, my coefficients are going to have, my estimated coefficients for my modeling are going to have multivariate normal distribution where I know that as long as I have the right model structure, the coefficients expected value will be, the estimated coefficients expected value will be the true correct coefficient values, and we're going to know what the variance covariance terms are in that multivariate normal. In a sense, from a statistics point of view, we know everything about the distribution when I have a large enough data set. All right, so under the appropriate conditions to have central limit theorem invoked for causal and invertible autoregressive moving average processes, the maximum likelihood and the unconditional least squares and the conditional least squares estimators, each initialized by the method of moments estimator, all provide optimal estimators for the white noise variance and those coefficients, in the sense that the white noise variance is consistent and the asymptotic distribution of our coefficient estimates is the best asymptotic normal distribution. Okay, so remember, when I say best, that's minimum variance. All right, so in particular, beta hat minus beta times square root of our sample size converges in distribution to normal, multivariate normal, with expected value of 0, and we have this funny covariance matrix. Okay, so you notice in the covariance matrix, first and foremost, I have my white noise variance times the inverse of a matrix. Now, if you've done a theory regression course, this should feel very similar to other situations with multivariate normal. All right, so the asymptotic variance covariance matrix of my estimators is going to be the inverse of this information matrix. All right, so notice that this matrix here, that whose inverse is here, is I'm going to represent with a block matrix. Notice that this has phi as the subscripts. This has theta theta. This has phi theta, and this has theta phi. All right, I'm going to do the easy stuff first. This is going to be the autocovariance of the coefficients for the autoregressive part. This is going to be for the coefficients of the moving average part, but we're going to be in the calculations. This is going to be the actual calculations themselves are going to be very similar to treating the moving average part as autoregressive. There's kind of a weird twist here. This part has a weird twist to it, and we'll see it in an example. Here, this is the cross covariance between the autoregressive part and the moving average part. And this is the transpose of this. Okay, so there is a lot going on. This is dense. This is juicy. This is good stuff. All right, the phi block is the autocovariance of the autoregressive process defined this way. The phi theta theta, this corresponds to the moving average. This is the autocovariance from taking an AR process, an autoregressive degree Q process. So I'm taking the moving average coefficients and I'm putting them into an autoregressive process here. All right, so notice that in these calculations, this equation means that we treat the moving average coefficients as coefficients in an autoregressive model, but there's going to be a sign change because of how we have things laid out when I move them over. Now here, this is going to be the cross covariance matrix between the coefficients for the autoregressive and the coefficients for the moving average. And the other block is the inverse of the other cross covariance. Okay, so now, that was a lot. That was a lot. I know you're saying, Smitty, let's break this down. Let's back up. Let's back up. Okay. Let's dip our toe into it. I know I just blasted you in the face with a fire hose. Let's do AR1. Let's take this theorem and apply it to AR1. All right, so what am I going to do? Well, I know from here, the expected value is the value I want it to be. The expected value of my estimate is the value that I'm trying to estimate. That's good. Now here, I know that I'm going to have inverse of that matrix times the white noise covariance. And now here, when I'm trying to deal with just beta, I can move this into here, into this portion, but I'm going to have to square it. Okay, so now what we're going to do, when I look at this part, if I only have one term, I only have one coefficient, I don't have anything else. This is going to be this big gamma is just going to correspond to this part because I don't have a moving average part. And then this block is just one coefficient. So this is a 1-by-1 matrix. Easiest type of matrix to work with. Okay, so now from the definition here, I know that I need I and j to be equal to 1. It's a 1-by-1 matrix. So this part is just equal to 0. This means that this is just going to be the auto covariance of a shift of 0, which is the variance of the entire process. Well, we've already worked that out. Boom, I've got it. All right, so now I know that I need to take an inverse. I need to multiply by sigma squared. Boom, I've got the variance of my coefficients after I do the divide by n part. So remember, here I have n squared. I have n squared. All right, so now when I'm only interested in the estimator by itself, so I'm interested in the estimator by itself, I have to do something with this n squared. I treat it as a constant, bring it into the variance, and so I know that I'm gonna have to divide and square it, and you notice that it pops in right there. And so now I know the asymptotic distribution of an AR1 coefficient. All right, that's good. So now let's do AR2. Now for AR2, what I'm going to do is I'm going to sit down and I'm going to look at the equations I get when I look at autocovariance. Okay, so if I sit down, I take the autocovariance equations where we have 0, we have 1, and we have 2. So notice that here in my autocovariance equations, remember from the Yule-Walker estimates, I have 2 minus 1 minus 1 as I go down. So 2, 1, 0. Now here, this is 1 minus 1 minus 1. Okay, so here, this is actually a negative 1, but when I deal with autocovariance, a negative 1 shift or a positive 1 shift are the same thing. So this, which should be a negative 1, is the same as gamma of 1. All right, so now let's do the same game. I'm going to have 0, shift by 1, so I'm subtracting 1, so that's a negative 1, but negative 1 autocovariance is the same as positive 1. Subtract again, I get a negative 2, but remember, negative 2, same as positive 1, and so then I get my auto covariance equation. So now I've got a system of equations. Boom, I can solve this. All right, so working it out, I'm going to skip some of the details here because this did take up quite a bit of paper for me to work out. All right, so if I look here, I can solve gamma of 1 in terms of gamma of 0 by subtracting and dividing. Real easy peasy lemon squeezy, boom, I get it. All right, now, once I have this representation of gamma of 1, I can slap that into this equation here, and boom, I can solve for gamma of 2 with respect to gamma of 0. Boom, I've got this. So now I'm going to go up to this equation. I'm going to plug in both of these into the equation, and I'm going to solve. Boom, I know, when I replace this with this part, I replace this with this part, I know that I'm going to have everything with respect to gamma of 0 and sigma squared. I do my college algebra. Boom, I know the relationship between gamma of 0 and sigma squared. All right, so now what I'm going to do is I'm going to take these and I'm going to put them onto that gamma matrix that we talked about. All right, so by the definition, I want this to be gamma of 0, gamma of 0. This is gamma of 1, and this is gamma of 1. It's going to be a symmetric matrix. All right, so I found when I was doing this pencil and paper, instead of putting the actual solutions, it was easier to leave gamma of 0 in there. So that's why I left it this way. When I do the upcoming calculations, this is an easier presentation than what I could have done, instead of having this here, I could have put this representation in there. Would have been exactly the same, but it's a little bit tougher sledding if you're going to go through and do the inverse. I went through, did the inverse myself, found it, and here we get it. It's the same value that's present in the textbook. So I always double check before I put it in. And so then I get this as my asymptotic distribution. You'll notice that this is a multivariate normal asymptotic distribution. So this is a bivariate normal. All right, so now I want to move on to moving average 1. When I do moving average 1, I have to treat the coefficient as an autoregressive coefficient, but I'm moving things around to balance out that equation, and so there's a little bit of a sign difference. All right, and so when I do that, things work out very nicely, and basically I just treat it exactly the same trick I did before. Okay, and so now for moving average 2, it's the same trick as before, but you'll notice that I've got a sign change here comparatively, but everything ends up being the same trick, the same method. I did this pencil and paper also and confirmed it. Now, if I want to do autoregressive moving average 1-1 model, all right, so here, when I think about this, I know that let's go up to our theorem, our block matrix. Here, when I do this part, I'm going to have my autoregressive part. I'm going to have my moving average part. Then I'm going to have the cross covariance between moving average and autoregressive. Okay, so it's an ARIMA 1-1. So this is going to be a 1-by-1 matrix. This is going to be a 1-by-1 matrix. And so I only have one term each. So to make this work out, this is also going to be a 1-by-1 matrix. All right, so the autoregressive part, I'm going to treat it just like I did with AR1. The MA1 part, I'm going to treat that just like I did with the MA1 part. So this part's super easy. The cross covariance, I'm going to have to do a little bit of extra work for. But once I get this one for free because they're transposed. 1-by-1 transpose are equal to each other. All right, so now this part is easy peasy. I'm just doing the same trick I did a moment ago, just slapping that down. And I'm just going to go ahead and, for the moment, leave the cross covariance aspect right there. All right, so now to get the covariance aspects, I'm just writing it out the way it is, and I'm going to invoke those backshift operator equations. I'm going to replace x of t with the backshift operator equation that we had when we set up the formulas previously. I'm going to replace the y sub t with the backshift operator formula we had also. All right, so now you'll notice I have the covariance of an addition, covariance of an addition. All right, so this will in fact break up into 4 covariances. But realize that when I have the white noise term, white noise with other indices, so non-matching indices like t minus 1, they're going to be 0. So 4 of those terms are, or excuse me, 2 of the 4 terms are automatically equal to 0. What's not going to be equal to 0 is the covariance between these guys and the covariance between the white noise terms. If I expand this out using my theoretical statistics course. All right, well, the part for here, I just write it out this way. The part here, I know that that's just going to be the auto covariance of the white noise without shifting, which is sigma squared. All right, and so now I realize that here I've got the same subscripts, so this is in fact the cross covariance I'm trying to find. So check this out. This is equal to that. So I can just go ahead and use some college algebra and solve. Boom, I've got it. I slap that into here. So now, and this next step is not in the textbook. I slugged through this. I've got this beautiful matrix. I need to take its inverse. It's 2 by 2, so it's not that bad of an inverse. I'm going to, on the diagonal, switch the positions, and then I'm going to take the negative of the off-diagonal parts. But remember, I have to divide by the derivative, and dividing by the derivative is where this gets to be a good, juicy college algebra problem. And so I do that, and a lot of things are going to cancel out. A lot of things are going to work out. It's going to be very nice. It's going to be beautiful. And I'm going to end up getting this whole term here. All right. So I double checked. We cannot simplify this matrix any further. We get this part multiplied by this 2 by 2 matrix as our covariance matrix for our asymptotic normal for ARIMA 11 model. And so there we have it. Isn't that beautiful? And something we can see, this is in fact a bivariate normal. Very nice. All right, well, that's all I've got for you. I hope you've enjoyed this. This has been a heck of a video. I'm super pumped up and excited. I'm gonna have trouble sleeping now. I'm so excited. But I'll see you next time. Life is short. Do math.